Our solar system is the most thoroughly mapped region of space in the universe. We have charted its planets, measured its moons, catalogued its asteroids, and traced the orbits of comets back to their frozen reservoirs. We know where everything is supposed to be. The maps have been drawn by generations of astronomers, each layer of precision added by another instrument, another theory, another mind bent on reducing the unknown. We have sent spacecraft to every planet. We have landed on asteroids. We have returned samples from comets. We know the temperature of Pluto. We know the composition of Titan's lakes. We have seen the surface of a world 1 billion kilometers away in sharper detail than our own ancestors saw the far side of their own continent. And yet, every few years, something appears that does not follow the rules. An object from another star system that accelerates without explanation. A six-sided storm at Saturn's North Pole that refuses to break apart. Moons with impossible shapes, impossible ridges, impossible oceans that should not be liquid. A gravitational pull in the outer dark that we can feel but cannot see. And a signal from the sky that came once, spoke clearly, and never returned. Consider what it means to stand at this edge. We have mapped the solar system with extraordinary fidelity, and still, the anomalies slip through. They are not failures of measurement. They are not errors in the data. They are real objects, real signals, real forces that our models cannot accommodate. Every time we think we have finished the map, the universe hands us a piece of territory that does not belong on it. You're going to walk through each of these anomalies, not to solve them, not to declare them artificial or natural, but to sit with the question of what they mean. Because the universe keeps handing us evidence that our models are incomplete. And the gaps between what we expect and what we find are where the real story lives. If thoughts about space keeps you up at night, hit like and subscribe before we begin. Now, take a breath. Let's start. On the 19th of October, 2017, a small telescope perched on the summit of Haleakala in Hawaii was doing what it always does. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS for short, scans the sky every night looking for moving objects. Asteroids, mostly. Comets occasionally. Nothing unusual. But on that night, a graduate student named Rob Werrick noticed something odd in the data. A faint point of light was moving too fast. Not fast for an asteroid. Fast for something that was not from here. Within days, astronomers around the world had calculated its trajectory. The orbit was hyperbolic. That one word changes everything. A hyperbolic orbit means the object is not bound to the sun's gravity. It came from somewhere else, passed through our neighborhood, and is now leaving forever. It was the first confirmed interstellar object ever detected inside our solar system. Here is the part that should stop you. If PAN-STARRS had been pointed at a slightly different patch of sky for just 1 hour, we would have missed it entirely. 1 hour. That's how close we came to never knowing this object existed at all. They named it Oumuamua. It is a Hawaiian word meaning scout or messenger from afar arriving first. The name was chosen because the telescope that found it sits on Hawaiian ground, but it also fits something deeper. This object was a messenger. The question is what it was trying to tell us. As astronomers tracked Oumuamua across the sky, they noticed something strange about its brightness. Most objects in the solar system, when you measure their reflected sunlight over time, show a gentle rise and fall, a slow pulse as they rotate, with the brightness changing by maybe 20 or 30%. Oumuamua did not do that. Its brightness changed by a factor of 10 Think about what that means. If you look at a football from one angle, it catches a certain amount of light. Spin it lengthwise, and the amount of light it reflects barely changes. But if you look at a pencil from the end, then spin it to show its full length, the difference is enormous. Oumuamua was changing its brightness by that kind of factor. The only way to produce that variation was an extreme shape, something 10 times longer than it was wide. A cosmic cigar. Nothing in our solar system looks like that. The most elongated asteroids we have ever seen barely reach a ratio of 3:1. Most are closer to 2:1, lumpy potatoes with no particular orientation. Oumuamua was an order of magnitude more extreme. It did not fit any category we had. Later, modeling suggested something even stranger. Some researchers argued the light curve could also be explained by an oblate shape. A pancake? Flat, thin, rotating end over end. That is equally unprecedented. No natural asteroid or comet has ever been observed with that geometry. Either way, the shape was wrong. It did not belong to the population of objects we know, and it was tumbling, not spinning cleanly, around a single axis, like a well-behaved asteroid. Chaotic rotation, flipping end over end, with no fixed axis of rotation. Most small bodies in the solar system are rubble piles, loose collections of rock and dust held together by gravity. When they tumble, they flex, they settle down. Oumuamua was rigid. It did not flex, it did not settle. It just kept tumbling, a solid object with no give, no internal damping. The shape alone would have been enough to mark it as unusual. But the shape was only the beginning. In June 2018, a paper appeared in the journal Nature. The lead author was Marco Micheli, and the team included astronomers from across Europe and the United States. They had collected 818 individual data points on Oumuamua's position over 29 days. They had traced its trajectory with extraordinary precision. And they found something that should not exist, a non-gravitational acceleration. A push. Something was changing Oumuamua's path in a way that gravity alone could not explain. The acceleration was tiny. 2.5 times 10 to the minus 4 centimeters per second squared. That is roughly housed 1,000th of the sun's gravitational pull at that distance. Tiny. But the measurement was rock solid. The team had assembled 818 individual astrometric measurements across 29 days of observation, drawn from a coordinated campaign that mobilized some of the most powerful instruments on the planet and in space. The European Southern Observatory's Very Large Telescope in Chile tracked Oumuamua across multiple nights, its 8-meter mirrors capturing the faint speck as it moved against the fixed stars. The Canada-France-Hawaii telescope on Mauna Kea contributed high-precision position data from its wide-field camera. The Hubble Space Telescope was called in for its unmatched resolving power, able to fix the object's location to within a few hundred kilometers at a distance of over 200 million kilometers. Even the Spitzer Space Telescope, designed for infrared astronomy and not normally used for tracking moving targets, joined the campaign, searching for thermal emission that never came. Each instrument independently confirmed the same deviation from the expected trajectory. Systematic errors from the solar wind, radiation pressure on the observatory platforms, and the Yarkovsky effect were all modeled and ruled out. When every dataset was combined and fitted against a purely gravitational trajectory, the residual was undeniable. The statistical significance was 30 sigma. In physics, 5 sigma is the threshold for a discovery. 30 sigma is not just a detection, it is a certainty. You could run the numbers for the age of the universe and the pattern would not appear by chance. Something was pushing Oumuamua away from the sun. The natural explanation. The first thing any astronomer would reach for is cometary outgassing. When a comet approaches the sun, its ices vaporize. The gas jets off the surface, acting like a rocket engine, nudging the comet off its gravitational path. It happens all the time. Standard physics, nothing mysterious. But Oumuamua showed no evidence of outgassing, no visible coma, no dust tail, no detected volatiles. The Spitzer Space Telescope searched for carbon dioxide and carbon monoxide, the most common cometary gases after water. Nothing. The Hubble Space Telescope looked for any extended cloud of material around the object. Nothing. No dust, no gas, no vapor. The object was completely clean. And there was the spin problem. If outgassing were happening, the jets would create torque. They would spin the object up, change its rotation rate measurably over the observation period. The data showed no such change. Oumuamua's rotation remained steady, no torque. No spin up, no outgassing. So something was pushing it, and we could not see what. That is the moment the mystery deepens. A natural object with a shape we have never seen, exhibiting an acceleration we cannot explain, producing no visible trace of the mechanism driving it. Every known process in the solar system had been ruled out. The data was clean. The anomaly was real. Something was pushing Oumuamua, and it left no trace. When natural explanations fail, scientists do not give up. They reach further. They propose materials that have never been seen in forms that have never been observed, existing under conditions that barely exist anywhere in the universe. That is where Seligman and Laughlin went in 2019. They suggested Oumuamua might be made of solid molecular hydrogen, ice. Here is the problem with that idea. Hydrogen is the lightest element in the universe. It does not freeze into a solid unless the temperature drops below 3 Kelvin. That is colder than the cosmic microwave background. Colder than the average temperature of empty space between the stars. The only place in the universe where H0 ice can form and survive is inside the densest, coldest regions of molecular clouds, the birthplaces of stars. If Oumuamua was a chunk of solid hydrogen, it would have to have formed in one of those clouds. It would have spent millions of years drifting through interstellar space at temperatures just above absolute zero. Then, as it entered our solar system and approached the sun, the H0 ice would begin to sublimate. Not melt into liquid. Sublimate. Turn directly from solid to gas at extremely low temperatures. That sublimation would produce a push, a gentle, steady acceleration without any visible trail. No dust, no coma, no tail. Just the faint release of invisible hydrogen gas. The mathematics worked. The acceleration profile matched. But there is a reason this hypothesis remains on the fringe. No such object has ever been observed. Not in our solar system. Not anywhere in the universe. No telescope has ever detected a chunk of solid hydrogen ice floating through space. The formation efficiency for such objects is vanishingly small. You need the right density, the right temperature, the right timing, and the right ejection mechanism to kick one out of a molecular cloud. The probability of all those conditions aligning to produce an object that then finds its way into our solar system is low enough to make most astronomers uncomfortable. A competing hypothesis has gained ground in recent years, and it comes from a different direction entirely. In 2021, Researchers Alan Jackson and Stephen Desch proposed that Oumuamua might be a chunk of solid nitrogen ice. Nitrogen is the primary component of the surface of Pluto and Neptune's moon Triton. If a Pluto-like exoplanet suffered a large impact early in its history, fragments of its nitrogen crust could have been ejected into interstellar space. The numbers work differently than the hydrogen model. Nitrogen ice sublimes at higher temperatures, around 55 Kelvin instead of 3. That means the acceleration would have begun farther from the Sun and followed a slightly different profile, ramping up as the object warmed. The observed data is consistent with both models, but the nitrogen hypothesis has a clear advantage. We know nitrogen ice exists on planetary surfaces. We have seen it with our own telescopes on Pluto and Triton, vast plains of frozen nitrogen stretching across hundreds of kilometers. We know that large impacts can eject material from a planetary surface into space. The formation pathway requires fewer theoretical leaps and rests on processes we have observed directly in our own solar system. There is a catch. A recent impact, large enough to eject a fragment the size of Oumuamua, would have produced a debris field, not a single intact fragment. If Oumuamua was a nitrogen iceberg, it should have had company. Other fragments, similar in composition, should have arrived around the same time. We have not found them. The nitrogen model explains the object itself. It does not explain why we only saw one. It is a theoretical patch, a way to make the numbers work without invoking anything truly exotic. But it stretches the definition of plausible to its breaking point. Then there is the other possibility, the one that made headlines, the one that got Avi Loeb called every name in the astronomical dictionary. In 2018, Loeb and his collaborator Shmuel Bialy published a paper asking a simple question. What if Oumuamua was not natural at all? What if it was artificial? Their proposal was specific. They suggested Oumuamua could be a light sail, a thin structure less than a millimeter thick, pushed through space by the pressure of sunlight. The same principle that drives experimental spacecraft like Breakthrough Starshot, which plans to send tiny sails to Alpha Centauri within a generation. Here is why the idea fits. The acceleration we observed was best modeled as proportional to r phi Sierra, inverse square of the distance from the Sun. That is exactly the functional form of solar radiation pressure, not outgassing, which tends to follow a different pattern. Solar radiation pressure, photons bouncing off the reflective surface, pushing it gently outward. The mathematics matches perfectly. A light sail would produce no outgassing, no coma, no dust tail, no detectable volatiles. It would be rigid, not a rubble pile. It would tumble if damaged, or if its center of mass did not align with its center of pressure. And it would have an extreme aspect ratio. Exactly, the shape that best fits the light curve data. The backlash was immediate. The astronomical community did not just disagree with Loeb. They dismissed him. They called the hypothesis unscientific. They said it violated Occam's razor. They pointed out that extraordinary claims require extraordinary evidence, and that the evidence for a natural explanation, however stretched, was still stronger than the evidence for an artificial one. Loeb pushed back. He argued that the scientific method does not work by consensus. It works by following the evidence wherever it leads, even if the destination makes people uncomfortable. He said, the solar sail hypothesis. If we find more interstellar objects with similar properties, we can compare them. If Oumuamua was a broken piece of a larger structure, we might find other fragments. The hypothesis makes predictions. Breakthrough. Listen, the SETI initiative funded by Yuri Milner, pointed the Green Bank telescope at Oumuamua in December 2017. They scanned for radio signals across 4 frequency bands. They found nothing. Absolute silence. That does not rule out the artificial hypothesis. A dead light sail does not transmit. A fragment of a broken probe does not broadcast. But it does not help the case either. The silence is what you would expect from a natural object. It is also what you would expect from a dead machine. The solar sail hypothesis remains unproven. It also remains unfalsified. That is the uncomfortable truth at the heart of the Oumuamua mystery. Every natural explanation requires an exotic material we have never seen. The artificial explanation requires a leap of inference that the evidence does not fully support. Both are possible. Neither is confirmed. The object is gone, and it took its secrets with it. So where does that leave us? Oumuamua is gone now. It is traveling toward the constellation Pegasus at 26 kilometers per second, moving away from us at a speed that will never slow down, never turn around, never bring it back. We had one encounter, one brief window, one object that passed through our neighborhood and left us with more questions than answers. Here is what we know for certain. It came from outside the solar system. The orbit was hyperbolic. That is not contested. It is an interstellar object, the first one we ever confirmed. That classification is solid. Here is what we do not know: what it was made of, why it accelerated, why it looked the way it looked. Every natural explanation requires a material we have never seen in space. Solid hydrogen ice that cannot survive at normal interstellar temperatures. Nitrogen ice in quantities that should not exist. An ultraporous dust aggregate with properties no known comet has ever displayed. Each hypothesis works on paper. None of them have been observed in nature. The artificial explanation requires a different kind of leap. Not a leap of material science, but a leap of inference. It fits the data. It explains the acceleration and the shape and the lack of outgassing. But it requires us to accept something we have no direct evidence for. The Vera Rubin Observatory is coming online now. It will scan the entire southern sky every few nights, detecting anything that moves. When it is fully operational, astronomers expect it to find dozens of interstellar objects every year. Then we will have a sample. Then we can ask whether Oumuamua was typical or unique, whether its strangeness was a sign of something rare or something we simply had not seen enough of. We already know, in fact, that such encounters are not as rare as we once believed. In 2023, the United States Space Command officially confirmed that a meteor detected in 2014 near Papua New Guinea, designated C. Eneos the 8th of August 2014, originated from outside the solar system. Its impact velocity of 45 kilometers per second was too high for an object bound to the sun's gravity. The fireball was captured by US government sensors, declassified years later, and verified by a team led by Avi Loeb at Harvard. It was the first interstellar meteor ever identified, predating Oumuamua by 3 years. The object was small, barely a meter across, but its existence proved that interstellar material reaches our solar system far more frequently than models predicted. The estimated rate jumped from less than 1 per decade to several per year. That changes the context for everything we have discussed. If dozens of interstellar objects enter our system every year, most of them too small and too faint to detect, then Oumuamua was not a freak occurrence. It was the first member of a population. And here is the uncomfortable part. The first 2 interstellar objects we identified were both anomalous. One was a meteor that hit Earth. The other was a shape we cannot explain. Both were strangers. The sample size is 2. Both are strange. That may be a coincidence, or it may be a signal. Until then, Oumuamua stands alone. A single data point. A question mark in the shape of an object we could not explain. It came from somewhere. It left without telling us where. Now we turn to something that did not pass through. Something that has been here the whole time, waiting for us to notice. In November 1980, Voyager 1 was leaving Saturn. It had completed its primary mission, taken its images, measured the rings, and was now being flung upward out of the plane of the solar system for a final look back. As it turned its cameras toward the planet's north pole, it saw something that made the imaging team stop. A hexagon, a six-sided shape in the clouds, straight edges, sharp corners. It looked drawn. It looked like nothing a planet should produce. The feature spanned 30,000 kilometers across, wide enough to swallow 2 Earths side by side with room to spare. The jet stream that formed its perimeter was racing at 500 kilometers per hour, yet the edges stayed straight. The corners stayed sharp. The entire structure rotated as a single unit, like a wheel with 6 spokes you could not see. The imaging team assumed a glitch, a camera artifact, a data processing error. They checked everything: the calibration, the pointing, the telemetry. The hexagon was real. It was there, in the clouds of Saturn's north pole, perfectly geometric, completely unexplained. 9 months later, Voyager 2 arrived. It had taken a different trajectory, a slower path through the Saturn system. Its cameras were older, its resolution slightly different. But when it looked at the same north pole, it saw the same shape, same hexagon, same position, same straight edges. The feature had not drifted. It had not deformed. It had held its shape through the months between the 2 spacecraft, through the rotation of the planet, through whatever weather patterns churned beneath it. The hexagon was not a fluke. It was a permanent feature of Saturn's north pole. And it should not exist. Here is the problem. Fluids do not form straight lines. They curve, they spiral, they swirl into vortices, they break into turbulence. They do not make corners. You can watch smoke rise from a candle, water flow down a drain, air move across a wing. It all follows the same fundamental physics. Smooth, curving, chaotic at scale. Never straight, never angular. The hexagon is a standing Rossby wave. That is the technical name for a planetary scale wave that forms when a fluid rotates on a sphere. Earth has them too. They shape our jet streams, push weather systems around the globe, meander in wide loops. They never form perfect geometric figures. They bend, they wobble, they break apart. They do not hold straight edges for decades. The Rayleigh-Kuo criterion is the mathematical rule that governs whether a jet stream is stable. It is a threshold, a line in the sand. If the curvature of the wind profile exceeds a certain value relative to the planet's rotation, the jet should break apart into turbulence. It is not a suggestion. It is a prediction derived from the equations of fluid motion. Saturn's hexagon violates that criterion. The curvature of the jet exceeds the threshold by a factor of roughly 4 times the limit. 4 times the point at which the mathematics says the flow should become unstable. To understand why a factor of 4 matters, consider what the criterion actually measures. It compares 2 competing forces. The restoring force from the planet's rotation, which tries to keep the flow organized, and the shear force from the wind itself, which tries to tear it apart. When the shear exceeds the rotation by a certain amount, the flow becomes barotropically unstable. Any small perturbation, any tiny ripple in the wind, will grow exponentially. It will feed on the energy of the mean flow, amplify itself, and break the jet into a cascade of eddies. That is what the mathematics predicts. That is what happens in every other planetary atmosphere where this threshold is crossed. The hexagon crosses it by a factor of 4. The shear is 4 times stronger than the rotation's ability to contain it. The jet should be violently unstable. It should disintegrate within days. Instead, it sits there, smooth, straight, unbroken. The perturbations that should tear it apart never appear. Something is suppressing them, and we do not know what. By every known physical model, this jet should have broken apart. It should have decayed into a chaotic mess of eddies and vortices within days, weeks at most. It has not. It has held its shape for over 40 years. The numbers say it should not exist. The planet disagrees. In 2004, the Cassini spacecraft arrived at Saturn, carried a suite of instruments designed to see what Voyager had only glimpsed. But there was a problem. Saturn's North Pole was in winter darkness. The hexagon, if it was still there, was hidden in shadow. No visible light could reach it. No camera could see it. But Cassini had infrared eyes. The visual and infrared mapping spectrometer could see heat. And when it looked at the North Pole, the hexagon was there. It glowed from within. The warm interior of Saturn's atmosphere radiated upward, and the shape of the hexagon was imprinted on that thermal glow. It had not shifted. It had waited in the dark, holding its shape through years of absolute night. Then came the gravity measurements. During Cassini's final orbits, the grand finale, the spacecraft dove between Saturn and its rings, measuring the planet's gravitational field with unprecedented precision. The data revealed something unexpected. The winds that formed the hexagon were not a surface feature. They extended 8,000 kilometers deep into Saturn's atmosphere. 8,000 kilometers. That is roughly the distance from London to Tokyo. The hexagon is not a weather pattern. It is a deep structural column, a cylinder of organized motion reaching down into the planet's interior. Wind speeds along the jet reach 500 kilometers per hour. That is faster than any sustained wind on Earth, and the structure rotates with a steady period of 10 hours, 39 minutes, and 23 seconds. The same period, measured year after year, decade after decade. No slowdown, no change. The hexagon is not a shallow cloud feature. It is rooted in the deep atmosphere, connected to whatever drives Saturn's internal dynamics. And that connection is something we still do not understand. Saturn takes 29.5 years to orbit the Sun. That means each season on the ringed planet lasts roughly 7 Earth years. 7 years of spring, 7 years of summer, 7 years of autumn. A full cycle of seasonal change plays out over the span of a human generation. From Voyager's flyby in 1980 through Cassini's final plunge in 2017, the hexagon survived 3 complete seasonal cycles. 3 times the North Pole went from spring to summer to autumn to winter. 3 times the amount of sunlight reaching that part of the atmosphere changed dramatically. 3 times the temperature gradients that drive weather patterns should have shifted. Here is the puzzle. When the Cassini team compared wind speeds measured between 2008 and 2012 with those recorded by Voyager in 1980 and 1981, they found no significant difference. The numbers matched within the margin of error. The jet had not slowed. It had not accelerated. It had not changed shape. The hexagon was the same structure Voyager had glimpsed decades earlier, as if the intervening years had not happened. That should be impossible. Seasonal changes alter the temperature balance of a planet's atmosphere. Warm air rises, cold air sinks, pressure gradients shift, jet streams meander. That is how weather works on any rotating planet with an atmosphere. Earth's jet streams move north and south by hundreds of kilometers as seasons change. Saturn's hexagon does not move at all. And then there is the asymmetry. Saturn's south pole has a polar vortex, a cyclone. It is round. It has an eye 50 times larger than a typical terrestrial hurricane. It spins, it churns. It does not form a hexagon. The southern pole has the same physical conditions as the north. Same gravity, same rotation rate, same atmosphere, same everything. But only one pole produces a perfect geometric figure. Why only one? No theory explains it. The southern hemisphere should be capable of forming the same structure. It does not. Something about the North Pole is different, and we do not know what. In a laboratory at Oxford University, researchers decided to build Saturn in a tank. Not the whole planet, of course, just the relevant part. A cylindrical container of water placed on a rotating table, spinning slowly to simulate the planet's rotation. A small ring in the center to mimic the polar region. Whole setup was a few feet across, not 30,000 kilometers. When the tank rotated at just the right speed, something remarkable happened. The surface of the water formed a hexagon, not a vague approximation, not a wobbly shape with 6 sides. A clear, sharp, geometric hexagon. The researchers had found a way to reproduce Saturn's anomaly in a lab. The experiment proved something important. Polygons can emerge naturally in rotating fluids under the right conditions. The hexagon is not a violation of physics. It is an extreme outcome of physics operating at the edge of a narrow parameter space. The tank experiment showed that differential rotation and shear can produce polygonal jet streams, square shapes. It depends on the exact balance of forces. The Oxford team mapped out the parameter space carefully. They varied the rotation rate of the tank, the temperature gradient between the center and the edge, and the depth of the water. They found that polygons only form within a narrow window. Spin the tank too fast, and the flow breaks into concentric rings. Spin it too slow, and nothing happens at all. Heat the center too much, and the water becomes turbulent. Heat it too little, and the pattern never emerges. The hexagon sits at a precise intersection of forces. A sweet spot where the rotation, the temperature gradient, and the fluid depth all align. Move any parameter by a few percent, and the shape vanishes. But here is the catch. The lab hexagon only persisted for a few hundred simulated days, a few hundred days of simulated time, and the shape began to break down. The parameters drifted, the edges softened, the structure decayed into the turbulence the equations predicted. The tank was a closed system. It had no way to replenish the energy that the hexagon consumed. Once the initial conditions started to degrade, the shape could not sustain itself. Saturn's hexagon has held for over 40 years, not a few hundred days, 40 years, without parameter drift, without shape degradation, without any sign that the jet is losing its coherence. The lab experiment shows that hexagons can form. It does not explain why one would last for half a human lifetime without changing. Saturn has something the tank does not. A continuous energy source, deep in the planet's interior, feeding the structure from below. The Oxford tank is a proof of concept. It tells us the hexagon is possible. It does not tell us why Saturn's version is so stable, so persistent, so resistant to every force that should tear it apart. The lab gave us a clue. The planet gave us a mystery. Every standing wave in a fluid requires a constant input of energy. That is a rule of physics. Without a continuous source pushing against friction and dissipation, any wave will eventually decay. Its energy converts to heat. Its structure blurs into background chaos. The hexagon has been holding its shape for over 40 years. Something is feeding it. The proposed mechanism is deep convection. Picture a pot of water on a stove. The bottom heats up, the water rises, reaches the surface, cools, and sinks back down. That cycle repeats as long as the heat is on. On Saturn, the internal heat left over from the planet's formation drives similar motions in the deep atmosphere. Hot gas rises from thousands of kilometers down, reaches the cloud tops, releases its energy, and sinks again. These convection cells, theorists propose, are what power the hexagon. They are the engine beneath the wave. There is a problem with this picture. We have never observed such cells. Models predict they should exist. The mathematics of heat transport in a giant planet atmosphere demands them. But no instrument has ever seen one. No thermal signature, no pressure anomaly, no direct evidence that these deep convection columns are real. They are a theoretical necessity, not an observed fact. Cassini carried instruments that could measure temperature at different depths, could map the distribution of ammonia clouds, probe the structure of the atmosphere at multiple pressure levels. If deep convection columns were rising beneath the hexagon, they should have left a thermal signature. Warm spot where the rising gas reached the cloud tops, a cold ring where the sinking gas returned to the depth. Cassini saw nothing like that. The temperature field around the hexagon was uniform. No hot plumes, no cold downdrafts. No sign of the convection that the models demand. Theorists have proposed that the convection cells might be too narrow to detect, or too deeply buried, or masked by the overlying cloud layers. Maybe the thermal signatures are there, but they are smeared out by the fast rotation of the planet, blended into a uniform background that looks smooth from above. Maybe the cells exist only in the deepest layers, thousands of kilometers down, where no instrument has ever looked. These are not explanations. They are excuses, ways of preserving the theory against the absence of evidence. And the Rayleigh-Coe criterion violation remains. The jet exceeds the stability threshold by a factor of 4. That gap has not been closed. Every attempt to explain it away runs into the same wall. The numbers say the jet should break apart. It does not. The models can approach the hexagon's behavior, can approximate its shape, can reproduce its general structure. They cannot capture its stability. The hexagon exists in a regime our physics can describe, but not explain. It is like looking at a building that stands despite every calculation, saying it should collapse. You can measure it, can photograph it. You can describe its features in precise detail. You cannot say why it is still there. Let us step back for a moment. Set aside the fluid dynamics, the Rossby waves, the convection cells. Consider the object itself. A perfect geometric figure, 30,000 kilometers across, centered on a planetary pole. Straight edges, sharp corners. Stable for decades, visible from interstellar distances. If you were designing a marker, something that could be seen from far away, something that would announce presence or claim territory, or simply say, "We were here," you might build something like this. A hexagon is a natural choice. It is the most efficient shape for tiling a plane. Bees use it, engineers use it. It appears in human architecture across cultures and centuries. If an intelligence wanted to leave a signature on a planet, a hexagon at the pole would not be a bad way to do it. But there is no evidence, no radio signals coming from the hexagon, no thermal anomalies that would suggest a solid structure embedded in the atmosphere, no spectral signatures of manufactured materials, no alloys, no polymers, nothing that does not belong in Saturn's natural chemical inventory. The hexagon is made of the same ammonia, ice, and hydrocarbon haze as the rest of the atmosphere. It is weather. It is almost certainly natural. Almost certainly. It carries the weight of everything we cannot explain. The stability, the geometry, the persistence through seasons that should have broken it. The fact that only one pole has it, the almost, is not evidence. A way of acknowledging that our models have a gap, and that gap is large enough to make us pause. The hexagon is probably natural. Probably. But the gap between probably and certainly is where the interesting questions live. And that gap has not shrunk in 40 years of observation, from a pattern in the clouds to patterns carved into solid worlds. In 1671, Giovanni Cassini pointed his telescope at Saturn. He named it Iapetus, after the Titan father of Prometheus in Greek mythology. Then something strange happened. The moon disappeared. Cassini could find it on one side of its orbit, but when it moved to the other side, it vanished completely. He would wait, watch, and eventually it would reappear as if emerging from a shadow that should not exist. Cassini deduced the truth. Iapetus was tidally locked. One hemisphere always faced forward in its orbit. One hemisphere always faced backward, and those two faces were not the same. The leading side, the one that plows through space, is dark. Extremely dark. As dark as fresh asphalt. It reflects only 3% of the light that hits it. The trailing side, the one that never takes the impact of micrometeorites and dust, is bright as fresh snow. It reflects 50% of the light. That alone is unusual. None have a contrast this extreme. None have a boundary this sharp. The line between dark and bright on Iapetus runs almost exactly along the meridian. It is not a gradual transition. It is a cut, a clean division between two worlds on a single body. The leading explanation is thermal segregation. The idea goes like this. Dark material, possibly from Saturn's outer moon Phoebe, drifts inward. The dark surface absorbs more sunlight than the bright ice. It heats up. The heat causes volatile ices within the dark material to sublimate, turning directly from solid to gas and retreating to colder regions. The process is self-reinforcing. Dark areas get darker as ice leaves. Bright areas get brighter as ice accumulates. Over millions of years, the contrast amplifies until you get what we see today. A moon split in half. The mathematics works. The model produces the right numbers, but it requires fine-tuned timing. The initial darkening agent has to arrive at just the right rate. The sublimation has to proceed at just the right speed. The process has to continue long enough to create the extreme contrast without ever being interrupted by a resurfacing event. It is a delicate balance, and the balance holds over billions of years. That is the natural explanation. It is plausible. It is mathematically consistent. It requires no exotic physics, but it also requires a series of conditions that line up with suspicious precision. The system works. The question is, whether it works too well. Now consider the ridge. Running along Iapetus equator for 3,000 kilometers is a mountain ridge, not a chain of peaks. A single continuous wall, 10 kilometers high. That is taller than Mount Everest, wrapping around the entire circumference of the moon like a seam. If you stood at the base of this ridge and looked up, you would see a wall of rock and ice rising vertically into the black sky. It does not taper. It does not break into separate formations. It runs straight, continuous for 3,000 kilometers. The ridge looks machined. The leading hypothesis for its formation is ancient, fast rotation. The idea is that Iapetus once spun much faster than it does today. A rapid rotation would have caused the moon to bulge at its equator, just as Earth bulges slightly at its equator from its own spin. If that bulge froze while Iapetus was still warm and malleable, and if the moon then cooled and slowed down, the bulge would remain as a permanent feature. A frozen equatorial ridge. The ridge had to form early, while Iapetus was still geologically active, still warm enough to deform. If the ridge formed too late, after the moon had cooled and solidified, the equatorial bulge would not have been able to freeze into a permanent structure. It would have relaxed back into the shape of a normal sphere as the rotation slowed. And Iapetus did slow down. Today it rotates once every 79 days. Extremely slow. Too slow to maintain an equatorial bulge by centrifugal force. The moon had to have spun down dramatically since the ridge formed. But here is the catch. Iapetus is far from Saturn. Tidal forces from the planet are weak at that distance. Tidal braking, the mechanism that slows a moon's rotation over time, should not have been strong enough to reduce Iapetus's spin from rapid to nearly stationary. The numbers do not add up. The ridge itself is heavily cratered. It is ancient, billions of years old. It has been sitting there, unchanged, since the early solar system. If the fast rotation hypothesis is correct, the ridge formed when Iapetus was still molten, froze in place, and then the rotation slowed through some mechanism we cannot fully explain. Orbital migration could account for the spin down, but that requires Iapetus to have moved closer to Saturn and then back out again. A series of unlikely events, each one possible, all of them together, stretching credulity. The leading hypothesis works like a house of cards. Remove one piece and it collapses. The ridge exists. It is real. It is ancient. It is continuous. And we do not have a clean explanation for why it is there. Iapetus today rotates once every 79 days. That is not a spin. It is a slow, stately turn, almost reluctant, as if the moon is barely bothering to show all its faces to Saturn. Most moons in the solar system spin much faster. Earth's moon takes 27 days. Even distant frozen worlds usually manage a rotation period measured in hours, not months. Tidal forces from Saturn should not have been strong enough to break its rotation this much at this distance. Iapetus orbits at nearly 2.5 million kilometers from Saturn. That is far. The gravitational grip is weak out there. Tidal braking, the mechanism that gradually steals rotational energy from a moon and transfers it into orbital motion, falls off sharply with distance. At Iapetus's orbit, the effect should be negligible. The moon should still be spinning relatively fast, still carrying the angular momentum it inherited from its formation, but it is not. Something slowed it down. The ridge is billions of years old. It is heavily cratered, ancient, unchanged, since the early solar system. For the ridge to have formed, Iapetus had to be rotating rapidly, while it was still warm and malleable. That means the fast rotation phase had to last long enough for the equatorial bulge to freeze into a permanent structure. Then, after the ridge was locked in place, the rotation had to slow to its current crawl. The timing window is tight. The fast rotation had to persist for the right amount of time. The spin down had to happen at the right rate. And the whole sequence had to unfold without interruption over billions of years. One proposed solution is orbital migration. Iapetus might have started closer to Saturn, where tidal forces were stronger, and then migrated outward over time. A closer orbit would have allowed stronger tidal braking, slowing the rotation more efficiently. Then, as Iapetus moved farther away, the braking would have stopped, leaving the Moon in its current slow spin state. It is a neat idea. It explains the numbers. But it requires Iapetus to have moved from a closer orbit to its current one, and the mechanism for that migration is unclear. It depends on interactions with other moons, with the rings, with the complex gravitational dance of the entire Saturn system. A series of unlikely events, each one possible, all of them together straining credulity. The leading hypothesis works like a house of cards. Remove one piece and it collapses. The ridge is real. The slow rotation is real. The connection between them is a story we tell ourselves. A narrative fits the data, but depends on conditions we cannot confirm. The Moon has a wall around its equator. It has a slow spin that should not exist. And we are still trying to connect the two. Now move inward. Closer to Saturn, where the tidal forces are stronger and the moons are smaller. Here sits Mimas, 400 kilometers across. A ball of ice with a crater on its face that should not be there. Herschel crater is 130 kilometers wide. That is 1/3 of Mimas' total diameter. Imagine an impact on Earth that left a crater spanning 4,000 kilometers. That is the scale we are talking about. A collision that punched a hole 1/3 of the way through the entire world. An impact that large should have shattered Mimas completely. The numbers are unforgiving. The kinetic energy released by an impactor of that size, traveling at typical collision velocities in the Saturn system, would have sent shockwaves racing through the Moon's interior. Those shockwaves would have fractured Mimas from core to surface. The Moon should have broken apart, scattered into a debris field, become a ring or a rubble pile instead of a solid body. Simulations confirm this. When researchers model the Herschel impact using the known properties of ice at the temperatures and pressures inside Mimas, the result is consistent. The shock waves propagate through the entire body. The fractures spread. The Moon should be cracked open like an egg. Yet Mimas is intact. It is smooth. It shows no global fracture networks, no chasms running across its surface, no signs that it was nearly destroyed and somehow held together. The crater is there, massive and deep, but the Moon around it appears untouched. The surface is heavily cratered by smaller impacts, but there are no radiating fracture patterns, no global stress lines, no evidence that the entire body was shaken to its core. Explanations exist. A low-velocity impact could have delivered less energy, reducing the shock. A highly porous interior could have absorbed the energy, compressing instead of fracturing. Both are possible. Both require special conditions. A low-velocity impact requires the impactor to have been moving unusually slowly relative to Mimas, which is unlikely in the chaotic environment of the early Saturn system. High porosity requires Mimas to have been a loose aggregation of ice particles rather than a solid body, which is difficult to reconcile with its current shape and density. The Moon survived. That is the fact. Everything else is a hypothesis built to explain that fact. The crater is there. The Moon is whole. The gap between what should have happened and what actually happened is large enough to make any explanation feel like a stretch. Then came the wobble. Cassini measured Mimas's rotation with enough precision to detect a libration, a small oscillation in the Moon's spin. The spacecraft's navigation cameras tracked surface features across multiple flybys, building up a time series of Mimas's orientation, accurate to within a few hundred meters. When the data was reduced, expected solid body rotation subtracted, a residual oscillation remained. It was larger than it should have been, larger than a solid body of that size and composition could produce. The amplitude was roughly 5 kilometers of surface displacement at the equator, a wobble big enough to see from orbit. The only explanation that fit the data was a subsurface ocean, 20 to 30 kilometers beneath the icy crust. A liquid layer, decoupling the surface from the core, allowing the shell to rock independently of the interior. Without that liquid interface, the tidal bulge would be locked to the core, and the libration would be negligible. The fact that it is measurable at all means the outer shell is floating. Mimas is cold. 70 Kelvin, that is minus 203 degrees Celsius. It is small, barely 400 kilometers across. It is heavily cratered, ancient, dead. It should be frozen solid all the way through. There should be no liquid water anywhere inside it. The thermal environment says no. The age of the surface says no. The size says no. The math does not add up. Tidal heating, the mechanism that keeps Enceladus warm and active, depends on orbital eccentricity and distance from the planet. Mimas has a higher eccentricity than Enceladus. It is closer to Saturn. By every calculation, Mimas should receive more tidal heating than its geyser-spewing neighbor. It should be warmer, more active, more alive. It is not. The surface is dead. No plumes, no smooth, resurfaced plains. No signs of internal activity at all. And yet the ocean is there. The wobble is real. The liquid water exists. The ocean is a fact. The heat source is a mystery. What does it mean to have an ocean 20 to 30 kilometers deep beneath a frozen crust? On Earth, that much liquid water would fill a basin the size of the Mediterranean Sea. On Mimas means a global ocean, a layer of water wrapping the entire Moon, trapped between an icy lid hundreds of kilometers thick and a rocky core. The pressure at the base of that ocean would be immense, hundreds of atmospheres. And where there is liquid water and pressure, there is the possibility of hydrothermal vents, if the core is warm enough to drive chemical reactions. Mimas joins a growing list of ocean worlds in the outer solar system. Europa, Enceladus, Titan, Ganymede, and now Mimas. But those worlds show signs of activity: plumes, fractured surfaces, magnetic signatures. Mimas shows nothing. The ocean is there. The heat source that keeps it liquid is not. And that gap between what we can detect and what we can explain is where the most interesting questions live. The leading candidate is tidal heating from a past orbital resonance, a phase when Mimas's orbit was more eccentric and the flexing was stronger. That heat would have taken time to propagate through the icy crust, and the ocean could be a lingering remnant, slowly freezing over millions of years. If that is the case, Mimas is a dying ocean world, its liquid layer thinning as the residual heat leaks away. The alternative is a recent orbital shift that initiated a new phase of tidal heating. Either way, the ocean exists now. Whether it will exist in a billion years is another question. Enceladus orbits at 238,000 kilometers from Saturn. Mimas orbits at 186,000. Enceladus is farther out, further from the planet's gravitational grip, further from the tidal forces that generate heat by flexing a moon's interior. And yet, Enceladus has active geysers shooting water vapor into space. A warm south pole, a global subsurface ocean, a surface that is geologically young and constantly being resurfaced. Mimas is closer. It should be flexed more. Its interior should be heated more. It should be more active than Enceladus, not less. The numbers predict the opposite of what we observe. Something is wrong with our understanding of Mimas' interior. The leading hypotheses are speculative. One possibility is that Mimas recently changed its orbit, perhaps within the last few 100 million years, and the tidal heating has not yet had time to manifest at the surface. A recent orbital shift could mean the interior is still warming up, the heat still propagating outward, the surface still cold and dead, while the deep interior slowly responds. It is possible. It is unprovable without knowing the orbital history. Another possibility is an unexpectedly high concentration of radioactive elements in Mimas's core. Radioactive decay generates heat. If Mimas has more rock, more heavy elements than its density suggests, the internal heat could be enough to maintain a subsurface ocean without tidal heating. But that would require Mimas to have formed with a composition that is unusual for a moon of its size and location. A special case, an outlier. Neither explanation is satisfying. Both are possible. Neither is confirmed. The gap between the numbers and the observation is where the interesting questions live, and that gap is large. Mimas has an ocean, should not have. It is cold and dead on the surface, warm and liquid within. The moon is a contradiction, and the contradiction has not been resolved. Now move farther out. Beyond the orbit of Titan, past the regular moons, into the region where Saturn's gravity grows weaker and the rules of the system start to fray. Here sits Hyperion. It does not look like a moon. It looks like pumice, a chunk of volcanic rock, irregular, pitted, almost porous in its texture. The porosity is estimated at 40%. That means nearly half of Hyperion's volume is empty space. A frozen, tumbling, electrically charged sponge. The shape is not spherical. It is not even roughly spherical. Hyperion is an irregular lump, its axes all different lengths, its surface covered in deep, sharp-rimmed craters that look more like erosion pits than impact basins. The whole thing looks like it was broken off a larger body and never smoothed out, and that is probably what happened. Hyperion is likely a fragment of a larger moon that was shattered by an impact sometime in the distant past. But if that is true, the parent body is gone, and we have no way to confirm the story. The rotation is the strangest part. Hyperion does not spin on a fixed axis. It tumbles. Its rotation period changes from week to week. One week, it might take 13 days to complete a turn. The next week, 18. There is no pattern. No predictability. The moon is chaotic in the strict mathematical sense. Its orientation at any future time is effectively impossible to calculate. The reason the chaos persists is Titan. Hyperion and Titan are locked in a 4-to-3 orbital resonance. For every 4 orbits, Hyperion completes, Titan completes 3. The gravitational pull from Titan, the second largest moon in the solar system, arrives at the same point in Hyperion's orbit every cycle. It acts like a hand reaching out and shoving the smaller moon off its axis each time it passes. The timing is precise. The effect is cumulative. Each shove adds a tiny amount of rotational energy, enough to overcome the internal friction that would otherwise damp the tumbling out. Without Titan, Hyperion would have settled into a regular spin within a few million years. With Titan, the chaos is permanent. This should not last. Gravitational forces from Saturn and from Titan, the massive moon that dominates the outer Saturn system, should gradually damp out the tumbling. Friction inside Hyperion should dissipate the rotational energy. Over millions of years, the moon should settle into a regular, predictable spin. It should synchronize with its orbit. It should become like every other moon in the system. It has not. The gravitational nudges from Titan, constant perturbations from the giant moon's immense gravity, keep Hyperion in its chaotic state. They inject energy into the rotation faster than friction can remove it. The tumbling is sustained, perpetual, frozen in a state that should be temporary but has persisted for billions of years. Then, there is the charge. Cassini's plasma spectrometer detected a steady beam of electrons streaming from Hyperion's surface into space. The moon is charged. As it tumbles through Saturn's magnetosphere, its irregular shape causes it to accumulate static electricity unevenly. One side builds up a negative charge while the other remains neutral. The potential difference grows until the surface can no longer hold it. Electrons leap from the moon into the surrounding plasma, creating a beam that Cassini's instruments could detect from hundreds of thousands of kilometers away. Hyperion is the only moon in the solar system confirmed to have this kind of electrical activity. It exists in a state that should be a brief phase in its evolution. It has been that way since before humans existed. And the hydrocarbon chemistry in its craters adds another layer of strangeness. The dark material lining the crater floors is rich in organic compounds, carbon-based molecules that form when ultraviolet radiation breaks down simpler ices on the surface. Cassini's spectrometers detected traces of methane, ethane, and more complex hydrocarbons frozen in the dark patches. The craters themselves are deep and sharp-rimmed, their shapes preserved by the moon's high porosity. When an impactor hits Hyperion, the energy is absorbed by the sponge-like interior instead of fracturing the surrounding terrain. That is why the craters look so fresh, as if they were carved yesterday rather than billions of years ago. The combination is unique in the solar system, a charged, tumbling, organic-rich sponge of a moon held in a state of permanent chaos by the gravity of its giant neighbor. From the moons, now leave Saturn behind. Travel outward, past the orbit of Jupiter, past the orbit of Saturn, past the orbit of Uranus and Neptune, until the Sun is a distant point of light and the planets are memories. Out here, beyond the last gas giant, the solar system becomes something else. Sparse, cold, dark, and strange. Beyond Neptune, at distances measured in hundreds of astronomical units, there is a population of icy bodies called extreme trans-Neptunian objects, ETNOs. They are the most distant things we have found in the solar system. Their orbits are vast, taking tens of thousands of years to complete a single lap around the Sun. And those orbits are not random. They cluster. Their longitudes of perihelion, the point in the orbit where each object comes closest to the Sun, are bunched together within a narrow arc. They should be spread evenly across the sky. Gravitational interactions with Neptune and the other giant planets should have randomized their orientations over the age of the solar system. That is what the models predict. That is what should have happened. It did not. The probability of this clustering occurring by chance is 0.007%. That is 3.8 sigma. In physics, 5 sigma is the threshold for a discovery. 3.8 sigma is not a discovery. It is a strong hint. A very strong hint. Something is herding these objects. Something massive. Something we cannot see. And there is more. The average orbital plane of these clustered objects is tilted by about 6 degrees relative to the ecliptic, the plane in which the 8 known planets orbit. That tilt is not explained by the known planets. Their combined gravitational influence pulls everything toward the ecliptic. The ETNOs should lie in that plane. They do not. Something is torquing the entire outer solar system, tilting the orbital plane of the most distant objects by a measurable angle. The orbital precession analysis from 2020 adds another layer. Researchers studying the long-term evolution of extreme trans-Neptunian objects found that their orbits are precessing, slowly rotating in space in a way that is consistent with a massive perturber at several hundred astronomical units. Without Planet 9, the precession rates should be uniform. They are not. The pattern of precession across the population points to the same hidden mass. It is an independent line of evidence derived from different data and different mathematics, yet it converges on the same conclusion. Something is out there. Something is herding these objects, shaping their orbits, pulling the plane of the system off its expected alignment. The evidence is statistical, it is gravitational, it is indirect, but it is real. And it points to a presence we have not yet seen. The only explanation that fits the data is a planet. Not a small one, a world 5 to 10 times the mass of Earth, orbiting between 400 and 800 astronomical units from the Sun. That is 10 to 20 times farther than Neptune. A dark world, magnitude 22 to 24. Beyond the reach of most surveys. Too faint for pan-stars. Too faint for the early sky scans. Hiding in plain sight, invisible to every telescope that has looked for it. Its orbit would be highly eccentric, stretched. At its closest approach to the Sun, it might come within 200 astronomical units. At its farthest, more than 1,000. One full revolution would take 10,000 to 20,000 years. The last time this planet was at its current position, human civilization was just beginning to form. The next time it returns, we will be gone. The gravitational influence of such a world would be subtle but profound. It creates what orbital dynamicists call a libration island, a safe harbor, a region of space where the gravitational forces balance in such a way that objects get trapped. They cannot leave. Their orbits become locked, their orientations fixed, their longitudes of perihelion clustered together in a narrow arc. Exactly what we observe. The mathematics is elegant, it is precise. It predicts specific orbital parameters, specific clustering patterns, specific inclinations. The planet's mass, distance, and eccentricity are not guesses. They are derived from the data. The equations produce a single solution that fits all the observed anomalies, the clustering, the tilt, the detached orbits, everything. The planet is predicted. It has not been found. Every new discovery tightens the case. Each time a survey finds another extreme trans-Neptunian object, its orbit is calculated, its position plotted, and the clustering pattern is checked. So far, every new object has fallen within the predicted arc. The cluster is not dispersing, it is consolidating. More data is making the anomaly stronger, not weaker. Consider 2015 BP 519, an object with an inclination of 54 degrees. That is extreme. Almost perpendicular to the plane of the solar system, objects like this should not exist in the outer solar system without a massive perturber to keep them stable. Neptune's gravity alone would have scattered it long ago, but it is there. And its orbit is exactly what Planet 9 models predict. The simulations produce it. The mathematics requires it. The discovery confirms it. Then came 2025. A new object was announced, catalogued as 2025 XX, with a perihelion of 66 astronomical units. A Sedna-like world, its closest approach to the Sun, placing it far beyond Neptune's gravitational reach. Its orbit was extreme, its inclination steep, its perihelion distance placing it squarely in the population that Planet 9 is predicted to shepherd. The discovery did not just add another data point to the cluster. It tightened the constraints on the planet's mass and orbit. Every new object narrows the parameter space. The planet cannot be too massive, or the shepherding would be too strong. It cannot be too distant, or the gravitational grip would be too weak. The new object, with its precisely measured orbit, pushed the allowed range into an even narrower corridor. The planet, if it exists, is becoming more precisely predicted with each discovery. The window is closing. Computer models of the outer solar system, run with a Planet 9 of the right mass and orbit, reproduce the observed alignment with remarkable fidelity. They generate the clustering. They produce the tilt. They create the detached orbits. They predict the high inclination objects. The simulations work. They match the data. The case is strong enough that many astronomers expect detection within the decade. The Vera Rubin Observatory, coming online now, will scan the entire southern sky with unprecedented depth. If Planet 9 is there, Rubin should find it. But prediction is not confirmation. It has not been found. The longer it stays hidden, the more the question burns. What if the clustering has another cause? What if the mathematics is beautiful but wrong? What if the planet is not there? Pan-STARRS, the Dark Energy Survey, the Catalina Sky Survey. Dozens of programs scanning the outer solar system year after year. They have found thousands of new objects. Asteroids, comets, Kuiper belt bodies, everything that moves against the fixed stars. They have mapped the distant reaches of our system in greater detail than ever before, and they have found nothing that matches the predicted planet. The sky is enormous. The predicted brightness range for Planet 9 is magnitude 22 to 24. That is extremely faint, visible only to the largest telescopes, and even then, only under perfect conditions. The planet could be hiding in the galactic plane, where the dense concentration of stars creates a wall of light that drowns out faint objects. It could be sitting in front of a background nebula, lost in the glow of interstellar gas. It could be anywhere along a vast arc of sky, and our surveys might have looked right at it without seeing it. It could be darker than expected. The albedo of a planet, the fraction of light it reflects, determines how bright it appears. Most planets in the solar system have albedos between 20 and 50%. They are relatively reflective. But a planet at 400 astronomical units, with a thick atmosphere of hydrogen and helium, could have an albedo much lower. It could be as dark as charcoal, absorbing most of the light that hits it, reflecting almost nothing. In that case, it would be invisible to optical telescopes. We would need infrared surveys to find it, and infrared surveys of the outer solar system are still in their infancy. The Vera-Rubin Observatory changes the equation. Its 8.4-meter mirror and 3.2 gigapixel camera will scan the entire southern sky every 3 to 4 nights, reaching magnitude 24.5 in a single exposure. That is deep enough to see Planet 9 if it is within the predicted brightness range. But there is a catch. Rubin's survey strategy is designed for transient detection, finding things that change position or brightness over time. A distant planet moves slowly, barely a few arcseconds per night. It will not show up as a moving object in a single night's data. It will require stacking images across weeks and months, subtracting the background of fixed stars, searching for the faint dot that creeps across the frame. The Rubin team has developed dedicated pipelines for this kind of slow-moving object detection. They expect to find hundreds of new Kuiper belt objects in the first year alone. If Planet 9 is there, within the observable range, Rubin should detect it within its first 2 to 3 years of full operations. If Rubin does not find it, the parameter space will shrink dramatically. The planet will be pushed to the very edge of plausibility, into orbits so distant and dark that no existing telescope could see it. The timeline is clear. Within the decade, we will know. Every null detection pushes the allowed parameter space further out. The planet cannot be too close, or we would have found it. It cannot be too bright, or we would have seen it. The absence of detection forces the models to retreat. The planet gets pushed farther away into darker, more distant regions where it is harder to confirm. The allowed mass range shifts upward. The allowed distance range expands. The planet becomes a moving target, receding as we search. The longer it stays hidden, the more the question burns. What if it is not there? What if the clustering has a different cause? What if the mathematics is elegant but wrong? The absence of detection does not disprove the hypothesis. It just makes it harder to maintain. And every year that passes without a sighting, the doubt grows a little louder. Some researchers have proposed an alternative. Not a planet, a disk. A dense concentration of dark matter in the outer solar system, distributed in a thin plane, exerting gravitational torques on the extreme trans-Neptunian objects. The idea is elegant in its simplicity. If dark matter clumps in the outer system, its gravity could herd the ETNOs just as a planet would. The clustering, tilt, the detached orbits, all could be explained without invoking a new world. The required density is the problem. To produce the observed gravitational effects, the dark matter disk would need a surface density orders of magnitude higher than current models predict. Dark matter in the solar system is measured by its gravitational influence on spacecraft. Voyager, Pioneer, New Horizons, all have traveled through the outer system, and their trajectories are known with exquisite precision. Any additional mass would have affected their paths. None was detected. The disk would need to be massive. Tens of Earth masses of dark matter, concentrated in a thin plane extending from beyond Neptune to the edge of the Sun's gravitational influence. That is not a wisp of exotic particles. That is a significant structure, and it would have other effects. It would heat the Kuiper belt through dynamical friction. It would alter the orbits of known objects in ways we could measure. It would produce annihilation signals, gamma rays from dark matter particles colliding, destroying each other. None of these signals have been detected. The dark matter disk is a theoretical placeholder. It fills the gap in our models without requiring a planet, but it requires a form of dark matter that behaves differently from everything we know. It is not a solution. It is a way of saying we do not have a solution. The gravitational anomaly is real. The clustering is real. The tilt is real. But the cause remains hidden. A planet, a disk, something else. We do not know, and until we find it, the outer solar system holds its secret. The detached orbits are the key. These are objects that never come close to Neptune. Their perihelia, the closest point in their orbit to the Sun, are well beyond Neptune's gravitational reach. They cannot have been scattered there by the known planets. Neptune's gravity can lift an object's perihelion, but only temporarily. Over millions of years, the pull of the gas giant should drag those orbits back inward. The objects should eventually cross Neptune's path and get flung out of the system entirely. They do not. They stay. Their perihelia remain high, stable, locked in place. Something is holding them there. Without a massive perturber, these orbits would scatter over billions of years. The gravitational influence of the giant planets, combined with the gentle pull of the galactic tide, would gradually randomize the orientations. The clustering would dissolve. The detached orbits would drift. The outer solar system would become a uniform, disorganized cloud of icy bodies, spread evenly across the sky. That is what the models predict. That is what should happen. It does not. The clustering persists. The detachment holds. The system is organized in a way that dynamics alone cannot explain. The planetary perturber creates a gravitational barrier. It is not a wall in the physical sense. It is a region of phase space, a set of orbital parameters where the forces balance in just the right way. Inside this region, objects are stable. Their orbits are protected. They can remain in their current state for billions of years, undisturbed by the chaos around them. Outside this region, objects are lost. They drift, scatter, get ejected into interstellar space, or pulled into the inner system where they meet a different fate. The dynamics demand a massive body. The numbers are clear. A planet of 5 to 10 Earth masses orbiting at 400 to 800 astronomical units with an eccentricity of about 0.6. Those are the parameters that produce the observed clustering. Those are the numbers that create the gravitational barrier. Those are the conditions required to shepherd the distant objects into their current configuration. The only question is what? A planet, a black hole, a dense clump of dark matter. The dynamics demand something massive. The identity of that something remains unknown, but the demand is real. The outer solar system is organized in a way that requires a shepherd. And until we find it, the mystery remains, from what pulls at the edges to what is missing at the wall. Now move to a different kind of edge. Not the edge of the clustered objects, but the edge of the Kuiper belt itself. The belt extends from about 30 astronomical units just beyond Neptune's orbit out to roughly 50 astronomical units. And then it stopped. Not gradually, not with a gentle taper. It drops off sharply. The Kuiper belt population falls off steeply at about 50 astronomical units. The number of objects per unit volume drops by a factor of 10 or more within a narrow band. It is not a gradual decline. It is not the expected thinning of a disk as you move away from the center. It is a war. A sudden, abrupt termination of the material that should be there. This is not how planetary disks work. A disk of material, whether it is a protoplanetary disk around a young star or a debris disk around a mature one, should thin out gradually. The density should decrease smoothly with distance. There should be a gentle gradient, a slow fade, a natural taper as you move away from the central body. That is how gravity works. That is how orbital dynamics works. That is how disks form and evolve. The Kuiper belt does not follow this rule. The drop-off is so abrupt it looks like a shear line. Something cut it off. Something removed the material beyond 50 astronomical units or prevented it from forming there in the first place. The edge is real. It has been measured. It has been confirmed by multiple surveys. The Kuiper cliff is not a contested observation. It is a fact. No known process in the standard model of solar system formation predicts this. The simulations of planetary formation, the models of disk evolution, the theories of how the solar system assembled itself from the primordial nebula. None of them produce a sharp edge at 50 astronomical units. They produce a gradual decline, a smooth gradient, a gentle fade, not a cliff. Kuiper cliff is a second gravitational mystery in the outer solar system. It sits alongside the clustering of the extreme trans-Neptunian object. It is separate from the Planet 9 anomaly, but it may be connected. Two puzzles, one outer system. The same question underlying both. What shaped the edge of our solar system? What cut it off so cleanly? If the primordial disk of material that formed the solar system extended beyond 50 astronomical units, and there is every reason to believe it did, we should see the evidence. A smooth decline. A gradual thinning of the population you move farther from the sun. The density of objects should decrease in a predictable way, following the same laws of orbital dynamics that govern every other disk in the universe. Simulations of the early solar system produce exactly that. A gentle gradient. A slow fade. The models run forward from the formation of the Sun, tracking the evolution of the protoplanetary disk as it coalesces, fragments, and settles into the Kuiper belt we see today. They all produce the same result. A gradual decline in object density with distance. Not a cliff, not a wall, a slope. The observations show something else entirely. The drop at 50 astronomical units is not a slope. It is a vertical face. The number of objects plummets by an order of magnitude within a narrow band. The missing mass is enormous. Dozens of Earth masses worth of material should be out there orbiting beyond the known edge of the Kuiper belt. It is gone. Where did it go? It did not just vanish. Material does not disappear from a planetary system without a cause. It can be ejected. It can be ground down into dust. It can be swept up by a passing body. But it cannot simply cease to exist. Something removed it. Something either stripped the outer Kuiper belt clean or prevented it from forming in the first place. The question is what? The leading explanation is a close encounter with another star. The Sun did not form in isolation. It was born in a cluster, a dense group of thousands of stars packed into a relatively small volume of space. In such an environment, close encounters between stars are not rare. They are expected. A passing star coming within a few hundred astronomical units of the young Sun could have gravitationally stripped the outer reaches of the protoplanetary disk. The physics is straightforward. Think of it like the Roche limit, the distance at which a moon gets torn apart by a planet's gravity. The same principle applies here, but on a far larger scale. When a star passes within a few hundred astronomical units, the difference in gravitational pull across the disk becomes extreme. The near side of the disk feels a stronger tug toward the passing star. The far side feels a weaker one, still anchored mostly to the Sun. That differential stretches the disk, pulling material away from the Sun's grip. It is not a gentle tug. It is a shearing force, a cosmic pair of scissors that rips the outer layers of the protoplanetary disk clean off. The material does not slowly drift away. It gets flung into interstellar space, scattered across light years, lost to the solar system forever. The result is a sharp cutoff at a specific distance, determined by the closest approach of the passing star. The edge is not gradual because the stripping is not gradual. Once the tidal force exceeds the sun's gravitational binding at that radius, everything beyond that point goes. The cut is clean. A cliff. We have direct evidence that such encounters happen. Look at the Orion Nebula, a star-forming region 1,000 light-years from here. The Hubble Space Telescope has imaged dozens of protoplanetary disks there, and many of them show clear signs of truncation. Disks with sharp outer edges, disks that are warped or tilted, disks that look like something sheared them off. In some cases, you can see the passing star itself, a bright companion that is clearly responsible for the damage. The Orion Nebula is a laboratory for exactly the kind of encounter that shaped our own solar system. The process is not theoretical. It is happening right now, in real time, in a stellar nursery we can observe directly. The sun likely formed in a cluster. Close encounters were common. The statistical probability of at least one such encounter during the first few million years of the solar system's existence is high. The shearing hypothesis explains the sharp edge. It explains the missing mass. It explains why the Kuiper belt ends so abruptly, as if a cosmic shear blade sliced through the disk at 50 astronomical units. But it is a scenario we cannot confirm without knowing which star passed by. The encounter would have happened 4.5 billion years ago. The star that did the shearing is long gone, scattered to a different part of the galaxy, its identity lost to the vastness of space. We can calculate the probability, we can simulate the gravitational dynamics, but we cannot point to a specific star and say, that one. It was that one. The evidence is circumstantial, the mathematics is sound. The confirmation is impossible. Here is where the two mysteries might touch: the Kuiper cliff and the orbital clustering of the extreme trans-Neptunian object. Two anomalies, one outer solar system. The same missing mass could explain both. Planet 9, if it exists, could dynamically clear the region beyond 50 astronomical units. Its gravitational influence would not just herd the extreme objects into their clustered orbits. It would also sweep the surrounding region clean. Objects that stray too close to its orbit would be scattered, ejected, or pushed into different configurations. Over billions of years, the planet would carve a gap in the Kuiper belt, a region of low density where few objects survive. The cliff at 50 astronomical units could be the edge of that cleared zone. Some models link both anomalies to a single massive perturber. The same planet that creates the libration island for the extreme objects also sculpts the inner edge of the outer Kuiper belt. The clustering and the cliff become two symptoms of the same cause: one perturber, two effects. A unified explanation for the strange structure of the outer solar system. The mathematics is elegant. A planet of the right mass, at the right distance, with the right eccentricity, would produce both the clustering and the cliff. The simulations bear this out. When you insert a Planet 9 into the models, the outer Kuiper belt develops a sharp edge. The objects beyond a certain distance get swept away. The remaining population clusters in the predicted arc. The two anomalies collapse into one mystery solving another. If the planet exists, that is the condition. The entire elegant structure, the unified explanation, the beautiful mathematics, all of it rests on a single assumption. A planet we have not found, a world we cannot see, a gravitational presence we infer but cannot confirm. The cliff and the clustering may be two symptoms of the same cause, or they may be unrelated, two separate mysteries. The solar system does not owe us simplicity. It does not have to be neat. The outer system could be strange for multiple reasons, each one independent of the others. The universe is not required to be elegant. It is only required to be what it is. The Kuiper Cliff is one of the least discussed anomalies in the solar system. It does not get the attention that Oumuamua gets. It does not generate the headlines that the hexagon generates. It is quiet. Technical, a feature of the outer system that most people have never heard of. But it is real, and it is unexplained. The edge is not a contested observation. Multiple surveys have confirmed it. The density of Kuiper belt objects drops sharply at about 50 astronomical units. The measurement is robust. The feature is real. What is contested is the explanation. A stellar flyby, a planetary perturber, something else entirely. The data cannot distinguish between the possibilities. The cliff exists. The cause is unknown. The outer solar system now holds at least two gravitational puzzles. The clustering of the extreme objects and the sharp edge of the Kuiper belt. Two anomalies, two features that the standard model of solar system formation cannot explain. Two questions that point to a missing piece of the story. The clustering demands a shepherd. The cliff demands a sculptor. Both could be the same object. A planet, a passing star, a dense disk of dark matter. The possibilities are narrowing as the data improves, but they have not converged. The outer system is keeping its secrets. Both puzzles point to a missing piece of the story. Something is out there. Something shaped the edge of our solar system. Something herded the distant objects into their clustered orbits. Something tilted the plane of the outer system. We cannot see it. We cannot confirm it. But we can feel its gravitational pull in the data. The mathematics is clear. The presence is inferred. The identity is unknown. The outer solar system is not empty. It is full of questions. And the questions are not problems to be solved. They are conditions to be lived with. The Kuiper Cliff stands at the edge of our knowledge. Beyond it, the darkness deepens. And somewhere in that darkness, the answer waits. In 1766, a German astronomer named Johann Titius noticed something strange about the planets. Their distances from the Sunday were not random. They followed a pattern. Each planet was roughly twice as far from the Sunday as the one before it. Mercury at 0.4 astronomical units, Venus at 0.7, Earth at 1.6. The numbers were not exact, but they were close. Close enough to make you wonder. Johann Bode, another German astronomer, popularized the pattern a few years later. He turned it into a formula. Start with 0.4. Add 0.3 times 2 to the power of n. For n equals negative infinity, you get 0.4. That is Mercury. For n equals 0, you get 0.7. Venus. For n equals 1, you get 1.0. Earth. For n equals 2, you get 1.6. Mars. For n equals 3, you get 2.8. That slot was empty. No planet had been found at that distance. Bode assumed it was waiting to be discovered. Then in 1781, William Herschel discovered Uranus. He calculated its orbit and found it at 19.2 astronomical units. The formula predicted 19.6. a near-perfect match. The Titius-Bode law looked like a genuine law of nature, a hidden order in the architecture of the solar system. The pattern was real. The empty slot at 2.8 astronomical units became a target. Astronomers searched for the missing planet. In 1801, they found Ceres, the first and largest asteroid. It sat at exactly 2.8 astronomical units. The slot was filled. The pattern held. The law predicted the existence of Uranus and the asteroid belt before anyone knew they were there. That is not coincidence. That is prediction. That is the kind of thing that makes a formula look like a discovery. Then came Neptune. Discovered in 1846, its orbit was calculated at 30 astronomical units. The formula predicted 38.8. A significant miss. Not close. Not a near-perfect match. The pattern that worked for 7 bodies broke at the 8th. A law of nature that fails 1/8 of the time is not a law. It is a coincidence. But a coincidence that works 7 times in a row across 200 million miles of empty space is a coincidence that demands an explanation. The Titius-Bode law has no physical basis. No known force of nature produces that specific mathematical relationship. No theory of planetary formation predicts it. It is a mathematical curiosity, a pattern that appears in the data without a clear reason. The planets are not required to follow it. They do not follow it perfectly. And in the case of Neptune, they do not follow it at all. But here is the strange part. Its accuracy for the inner solar system is statistically unlikely. The probability that 7 planets would fall so close to a simple exponential curve by chance alone is low. Not impossible, but low. The pattern could be real. It could reflect some underlying physical process that we do not yet understand. Or it could be a coincidence, a numerical accident, a trick of the mind that sees order where none exists. We have now discovered thousands of planets around other stars. Their architectures are diverse. Some systems have planets packed tightly together, their orbits separated by tiny gaps. Others have planets spread far apart with vast empty spaces between them. Some have resonant chains where the orbital periods of neighboring planets form simple integer ratios. Others have no discernible pattern at all. Our solar system, with its neat spacing and orderly arrangement, looks unusual compared to the chaos of the galaxy. We are an outlier. A quiet, ordered system in a universe of crowded, chaotic ones. Some astronomers argue that the Titius-Bode law reflects orbital resonances inherited from the protoplanetary disk. As the planets formed, gravitational interactions with the gas disk could have pushed them into specific orbital distances, creating the pattern we see. The mathematics of disk migration can produce spacing that approximates a geometric progression. It is not a law. It is a consequence of the formation process, a fossil of the early solar system preserved in the orbits of the planets. Others call it numerology, a mathematical pattern that humans impose on nature because we are pattern-seeking creatures. We see faces in clouds. We see shapes in constellations. We see order in numbers. The Titius-Bode law is a Rorschach test for our own desire to find meaning in the cosmos. It works for 7 bodies. It fails at the 8th. The failure is not a problem with the data. It is a problem with our need for patterns. The debate reveals something about us. We want the solar system to be ordered. We want the planets to follow a rule. We want the architecture to mean something. And when the data does not cooperate, we find ways to make it fit. We adjust the formula, we add exceptions, we call it a coincidence, and move on. But the question remains, why does the pattern work at all? Why does it hold for 7 bodies and break at the 8th? What is the universe telling us? Now look up. The moon hangs in the sky, familiar, constant, taken for granted. It has been there since before there were eyes to see it. But here is the thing about Earth's moon. The moon is 1.2% of Earth's mass. That number sounds small until you compare it to every other moon in the solar system. No other planet has a moon that large relative to its own size. Mars has Phobos and Deimos, tiny captured asteroids, each less than a millionth of the planet's mass. Jupiter has Ganymede, the largest moon in the solar system, but it is only 1/10,000th of Jupiter's mass. Saturn's Titan is similarly tiny compared to its parent. The moon is different. It is a companion, not a satellite. It is large enough that some astronomers consider the Earth-Moon system a double planet. The moon does something else. It stabilizes Earth's axial tilt. Without the moon, Earth's axis would wobble chaotically over millions of years, swinging from near-zero tilt to angles exceeding 60 degrees. That would mean extreme climate swings, ice ages that last for millions of years, followed by periods of intense heat, followed by more ice. The kind of instability that makes complex life difficult, if not impossible. It keeps the tilt at about 23.5 degrees, stable enough for seasons to cycle predictably, for climate to remain habitable over geological timescales. The moon may be the reason we are here. The leading explanation for its formation is the giant impact hypothesis. Early in the solar system's history, a Mars-sized body named Theia struck Earth. The collision was catastrophic. Theia's core, the outer layers of both bodies, were blasted into space, forming a disk of molten rock that eventually coalesced into the moon. The model fits many of the observations. Explains the moon's composition, its lack of a large iron core, its orbital distance. But there is a catch. The collision had to be at just the right angle. Too glancing, and Theia would have kept going, leaving Earth mostly intact, with no moon. Too direct, and both bodies would have been destroyed, forming a rubble field instead of a planet and its companion. Too slow, and the material would have fallen back to Earth. Too fast, and everything would have been ejected into space. The impact parameter, the angle, the speed, the mass ratio, all of them had to fall within a narrow window for the outcome to produce our exact moon. The probability of such a hit is low. Lucky shot. The solar system had 100 million years to get it right, and it did. But the odds were against it. The moon is a statistical anomaly, a near miss that became a direct hit, a catastrophe that created the conditions for life. Here is where the model gets uncomfortable. Simulations of giant impacts produce a wide range of outcomes. Most of them do not look like our moon. They create moons that are too small, orbiting too close to the planet, on unstable orbits that decay over millions of years. They produce disks that are too hot or too cold, material that falls back to Earth instead of accreting into a satellite. The parameter space for a successful Earth-Moon system is narrow. Most impacts fail. Earth's moon is both large and at a stable orbital distance. It is not slowly spiraling away, not crashing back toward the planet. It is in a Goldilocks orbit, far enough to be stable, close enough to exert its stabilizing influence on Earth's tilt. That is a specific outcome, not a generic one. The models have to be fine-tuned to produce it. The isotope ratios add another layer of difficulty. Earth and the moon have nearly identical isotopic compositions for many elements. Oxygen isotopes, titanium isotopes, silicon isotopes, they match almost perfectly. That is unusual. If the moon formed from a collision with a different body, you would expect some difference. Theia should have had a distinct isotopic signature, a chemical fingerprint from its own region of the solar system. The moon should carry traces of that fingerprint. It does not. The ratios are so close that some scientists argue the moon must have formed from Earth's own material, not from a mixture of Earth and Theia. This led to a new hypothesis. The synestia. A synestia is a donut-shaped cloud of vaporized rock, spinning so fast that it extends beyond the classical limit of a solid body. In this model, the impact did not create a disk of debris around a solid Earth. It vaporized both bodies entirely, turning them into a single, spinning cloud of molten and gaseous rock. The moon condensed from this cloud, drawing material from the entire structure, not just from Theia. That would explain the identical isotope ratios. Everything was mixed together before the moon formed. Either way, the conditions had to be exquisitely fine-tuned. The impact angle, the velocity, the mass ratio, the rotation rate, the cooling time, the accretion rate, all of them had to fall within a narrow range. Change any one parameter by a few %, and the outcome changes dramatically. No moon. A different moon. A moon that crashes back into Earth. A moon that drifts away into space. The fact that we have this particular moon at this particular distance with this particular stabilizing effect is a coincidence that strains credulity. It is not evidence of design. It is evidence of rarity. The solar system rolled the dice and it came up 7. But when you look at the odds, you start to wonder, how many Earth-like planets have moons like ours? How many have stable tilts, stable climates, stable surfaces? How many are lucky enough to have a companion that holds them steady for billions of years? The answer may be very few, and that makes Earth not just rare, it makes Earth strange. Now zoom out. Look at the galaxy. We have found thousands of exoplanets. We have mapped their orbits, measured their sizes, estimated their compositions. And what we have found does not look like home. The most common type of planet in the galaxy is the super-Earth, a world between Earth and Neptune in size, with a mass 2 to 10 times our own. These planets are everywhere. They orbit red dwarfs, yellow dwarfs, every kind of star we can see. They are packed into tight, compact systems, their orbits separated by tiny gaps. Some systems have 5, 6, 7 super-Earths, all within a region smaller than Mercury's orbit. They are crowded, chaotic. Nothing like the wide, empty spaces of our own system. Our solar system has no super-Earth. We have small, rocky worlds in the inner system and gas giants in the outer system. Nothing in between. That gap is unusual. The galaxy is full of planets in the size range we lack. We are missing an entire class of world that seems to be the galactic standard. Then there is the habitable zone. Our system has exactly one gas giant in the region where liquid water can exist. Jupiter. It sits at the edge of the habitable zone, its gravity sweeping the inner system clean of debris, protecting Earth from frequent impacts. Many exoplanet systems have gas giants much closer in, hot Jupiters orbiting their stars in days instead of years. Those systems are different. The inner planets are rare, scattered, disrupted by the giant's gravity. Our system is quiet, ordered. A single gas giant at the right distance doing its job without interference. We are an outlier. The data is clear. Most planetary systems do not look like ours. They are denser, more crowded, more chaotic. The galaxy is full of systems that defy the neat architecture we take for granted. Our solar system, with its wide orbital spacing, its missing super-Earths, its single gas giant at the edge of the habitable zone, is not the norm. It is the exception. Why is our architecture so different? There are two possibilities. One is that we are rare. The conditions that produced our system are uncommon. Most Earth-like planets form in different environments with different outcomes. The other is that our detection bias is hiding the truth. We find super-Earths because they are easier to detect. Small, widely spaced planets like ours are harder to see. The galaxy could be full of systems like ours, and we simply cannot see them yet. The answer is probably somewhere in between. But here is the unsettling possibility. Very order we take for granted may be the anomaly. The quiet, stable, well-behaved solar system we call home may be a statistical fluke, a rare configuration in a universe. We are not the standard. We are the outlier. And that changes how we see ourselves. Look back at what we have covered. The Titius-Bode pattern, the moon, the architecture of the system. These things look like they were arranged. They fit together in a way that feels intentional. The planets follow a mathematical sequence. The moon stabilizes the climate. The system is ordered in a way that seems to favor life. But no known law requires this arrangement. No force of nature demands that the planets follow the Titius-Bode sequence. No physical principle insists that Earth must have a large moon. No cosmic rule says the solar system must be quiet and orderly. The configuration we see is a contingent outcome. It could have been different. It almost certainly was different for most systems in the galaxy. The fact that it turned out this way is a roll of the dice that came up 7. Here is the question. If the solar system were designed, what would be different? If an intelligence had arranged the planets, placed the moon, tuned the architecture, what would we expect to see? Probably something very close to what we see. An ordered system, a stable climate, a large moon, planets spaced in a way that makes mathematical sense. The patterns we observe are exactly what you would expect from design. They are also exactly what you would expect from a rare but natural configuration. The two possibilities are observationally indistinguishable. Design and coincidence produce the same evidence when the sample size is 1. A universe built by intention and a universe that just happened to land on this result look identical until you have another example to compare against. We do not. That is where the Fermi paradox touches this question. If the solar system is unusually ordered and life-friendly, does that make Earth more surprising or less? The answer cuts both ways. A quiet, stable system with a perfect moon and a giant planet guarding the inner worlds makes life more likely here. So our existence becomes less surprising. The dice were loaded in our favor. But if such systems are rare across the galaxy, then the silence makes sense. We are here because we are in the one system where life could take hold. The rest of the galaxy is full of crowded, chaotic systems where complex life never gets a chance. The order that enabled us is the same order that isolates us. That is the paradox. The very conditions that make Earth special may be the reason the great silence persists. Perhaps the patterns are real. Perhaps we are not yet ready to understand them. The Titius-Bode law may be a clue to something deeper, a hidden structure in the formation of planetary systems that we have not yet decoded. The moon may be a sign that Earth is special. or it may be a coincidence that we read too much into. The architecture of the solar system may be telling us something, or it may be telling us nothing. This chapter does not conclude. It sets up the final mystery. The patterns are there. The question is whether they mean anything. We are pattern-seeking creatures. It is our greatest strength and our deepest weakness. We see order in chaos. We see meaning in noise. We see design in accident. The solar system is a mirror. It reflects back what we bring to it. And what we bring is a desperate need to understand. From the architecture of worlds to a single word on a printout. The Big Ear radio telescope sat in a field outside Columbus, Ohio. It was not the most glamorous instrument in the world. A massive aluminum dish, fixed to the ground, unable to move. It scanned the sky by letting the rotation of the Earth carry the stars across its focal point. Day after day, night after night, the same strip of sky, over and over again, waiting for something to happen. On the night of the 15th of August 1977, the telescope was doing what it always did, listening. The data came out on paper printouts, columns of letters, and numbers that represented the intensity of the radio signal at each frequency. A volunteer named Jerry Amon was going through the printouts, checking for anything unusual. It was tedious work, hours of staring at rows of alphanumeric code, looking for a pattern that did not belong. He found one. A sequence of letters and numbers jumped off the page. 6 characters, 6EQUJ5. The code meant something specific. Each character represented the intensity of the signal above the background noise, measured in units called sigmas. A space meant the signal was at the background level. A number meant it was above background. A letter meant it was far above. The sequence told the story. The signal rose from nothing to 6 sigmas in seconds. Then it peaked at the letter U, the highest value the system could record. Then it faded back to nothing. A single sharp spike in the data. 30 times the background noise. The frequency was 1420 megahertz. That number matters. 1420 megahertz is the natural emission frequency of neutral hydrogen, the most abundant element in the universe. It is the frequency that any astronomer, anywhere in the galaxy, would know to listen on. It is the universal calling channel. Emmon circled the sequence in red pen. He wrote a single word in the margin. Wow. The signal lasted exactly 72 seconds. That was the time it took for the telescope's beam to sweep across a point source in the sky. 72 seconds of data. Then silence. The signal never returned. The telescope scanned that exact same strip of sky thousands of times in the years that followed. Nothing. Every other telescope that pointed at those coordinates found the same thing. Absolute silence. Here is what made the WOW signal different from every other transient radio burst ever detected. Start with the frequency. 1420 megahertz is not random. It is the frequency that neutral hydrogen atoms emit when their electron spins flip from parallel to anti-parallel. It is a natural constant. Any civilization that understands radio astronomy would know this frequency. It is the obvious choice for a beacon, the cosmic equivalent of a public channel. The signal was narrowband, less than 10 kilohertz of bandwidth. That is the key. Natural radio sources produce broad, diffuse emissions. Stars, gas clouds, galaxies, they all emit across a wide range of frequencies. A narrowband signal requires engineering. It requires a transmitter. Nature does not produce a clean, tight signal at a single frequency. Not like this. Then there was the Doppler drift. When a source moves relative to Earth, its frequency shifts. A signal from a rotating planet, a moving spacecraft, an orbiting satellite, they all show a characteristic drift as the relative velocity changes. The WOW signal showed none. The frequency was stable for the entire 72 seconds, as if the source was stationary relative to Earth. That is almost impossible for a natural object. Planets move, stars move, galaxies move. Everything in the universe is in motion. A signal with no Doppler drift implies either a source that is perfectly aligned with Earth's motion, which is statistically absurd, or a source that was deliberately compensating for the drift. The second possibility is not natural. The source was in the constellation Sagittarius, near the galactic plane. That region contains thousands of star systems, hundreds of potential civilizations. It also contains gas clouds, nebulae, and the dense core of the Milky Way. A needle in a cosmic haystack. The signal came from somewhere in that region, we do not know where. The big ear had limited angular resolution. It could narrow the source to a patch of sky about the size of the full moon. That patch contains millions of stars. The coordinates are not precise enough to identify the specific source. Every attempt to find it again has failed. Telescopes around the world have pointed at those coordinates. The Allen Telescope Array, the Green Bank Telescope, the Lovell Telescope at Jodrell Bank, nothing. The Arecibo Observatory, before its collapse, searched the region multiple times. Silence. Breakthrough Listen, the most comprehensive SETI survey ever conducted, scanned the same patch of sky with instruments far more sensitive than the big ear. Nothing. The signal came, it spoke, and it never returned. That is the mystery. A single data point. A 72-second window into something we cannot explain. The universe gave us one chance. We took it. And then it closed. The silence that followed is the loudest thing we have ever heard. In 2024, a team of researchers published a reanalysis that proposed something new. A natural explanation. Not a transmission. Not a beacon. A cosmic accident.
Elliptical galaxies, once
Somewhere
thought to be
in the
featureless,
constellation
are now
Sagittarius,
revealing their
a
intricate
magnetar
connection
flare.
to the surrounding nebulae.
Magnetars are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. When they flare, they release more energy in a fraction of a second than the sun releases in 100,000 years. That radiation, traveling across space, passed through a cold cloud of neutral hydrogen. The hydrogen atoms absorbed the energy. Then they re-emitted it all at once in a narrow beam at exactly 1420 megahertz. Stimulated emission, a natural maser. The same physics that powers a laser, but on an interstellar scale. The numbers work. A magnetar flare of the right intensity, passing through a hydrogen cloud of the right density, at the right distance, would produce a signal that looks exactly like what the big ear detected. Narrowband, bright. At the hydrogen line, no Doppler drift, because the cloud is stationary relative to the background. The signal would last as long as
This
the cloud
incredible
lasted,
fly-through
or as long
reveals
as
the sheer
beam swept
scale of the
across Earth,
cosmos,
whichever came
a
first.
tapestry of billions
72
of
seconds.
suns.
Then silence. It is a clean explanation. It accounts for every observed property of the WOW signal. The frequency, the bandwidth, the duration, the intensity, the failure to repeat. All of it fits within known physics. No aliens required, no exotic technology. Just a rare alignment of natural events, producing a signal that looked artificial, but was not. There is one problem. No magnetar has been identified in that direction. The region of sky where the signal originated has been searched. No known magnetar sits within the error box. No known magnetar flare was recorded at that time. The explanation requires a magnetar that we cannot see, producing a flare that we did not detect. illuminating a hydrogen cloud that we cannot confirm, in a direction that we cannot verify. It is plausible. It is unconfirmed. It is a story we tell ourselves to make the anomaly go away. Since 2024, no similar event has been detected. No other arrowband burst at the hydrogen line triggered by a magnetar flare. If this is a natural phenomenon, it is extraordinarily rare. 1 in a million alignment of conditions that happens once in a generation, if that. The universe is full of rare events. This could be one of them. Or it could be something else. The magnetar hypothesis is not proven. It is not disproven. It sits in the gray zone, the space between explanation and speculation, where most of the interesting questions live. It is a natural explanation that requires unnatural luck, and that is the pattern we keep seeing. The universe produces anomalies that can be explained, but only by stretching the definition of probable. Breakthrough Listen is the most ambitious SETI program ever undertaken. Funded by Yuri Milner, backed by Stephen Hawking, it has surveyed millions of stars across thousands of hours of observation. It has scanned the galactic plane. It has listened to the nearest thousand sun-like stars. It has searched for laser pulses, radio transmissions, and every other technosignature we can imagine. It has found nothing. The great silence stretches across every frequency, every direction. Not a single confirmed artificial signal has been detected in over 60 years of searching. The universe is quiet, not silent in the absolute sense. There is background radiation. There are pulsars. There are gas clouds emitting their natural frequencies. But the kind of signal that would indicate intelligence, the kind that would make us sit up and say, someone is out there, that signal has not come. If the wow signal was natural, it was a 1 in a million event. A freak alignment of a magnetar and a hydrogen cloud, producing a transient burst that fooled us into thinking we had found something. The probability of such an event occurring is low, but the universe is large. Low probability events happen all the time. We just happen to be the ones who saw this one. If it was artificial, whoever sent it stopped transmitting. A civilization capable of broadcasting a narrowband signal at the hydrogen line would know how to aim it. They would know that a signal aimed at Earth would take years to arrive. They would know that if they wanted a reply, they would have to keep transmitting, but they did not. The signal came once. It never repeated. That could mean the source was destroyed. It could mean the source was never there in the first place. Or it could mean the source was not a civilization at all. Silence is evidence of absence. It is not proof of nothing. The universe is vast. We have scanned a tiny fraction of the sky, at a tiny fraction of the frequencies, for a tiny fraction of the time. The silence could mean we are alone. It could mean no one is broadcasting. It could mean everyone is listening. It could mean the signals are there and we are not yet smart enough to recognize them. The great silence is the loudest thing we have ever heard. It fills every observation, every search, every null result. It is the background against which every anomaly stands out, and it is the thing that makes the wow signal so strange. One signal in 60 years of listening. One moment of something that looked like contact, and then nothing. The silence closed in, and it has not opened again. In 1974, a team of scientists at the Arecibo Observatory did something remarkable. They pointed the telescope at the globular cluster M13, 25,000 light years away. And they sent a message, a binary encoded transmission containing information about our solar system, our DNA, our species. Digital postcard aimed at a cluster of 300,000 stars. It was a gesture, a symbolic act, a way of saying, we are here. The message will take 25,000 years to arrive. If anyone in M13 receives it, decodes it, understands it, and decides to reply, that reply will take another 25,000 years to reach us. 50,000 years for a single exchange. That is not communication. That is a time capsule thrown into the ocean with no return address. But here is the strange part. We sent that message. We pointed our most powerful transmitter at a distant star cluster and broadcast our existence to the universe. We are a source. We are a transmitter. We are the thing we are looking for. The asymmetry is stark. We listen for signals from other civilizations, but we have already sent our own. We have announced our presence. We have given away our coordinates. We are both the hunter and the hunted, the listener and the broadcaster, the one who waits and the one who speaks. The wow signal may have been a reply to a message we never knew was sent. Somewhere out there, a civilization may have detected a transmission from Earth, a signal we forgot we broadcast, a beacon we lit without knowing. They replied. Their reply arrived on the 15th of August, 1977, at 1420 MHz, 72 seconds of data that we caught and then lost. We heard their answer, but we did not recognize the question. That idea changes everything. We are active participants in a conversation we do not fully understand. We have sent messages into the void, hoping someone is listening, and we have received a message back. Maybe. The wow signal could be the reply. A single word in a dialogue that spans millennia. We spoke, something answered, and we have been trying to make sense of the answer ever since. There is another possibility, one that does not involve magnetars or hydrogen masers or rare alignments of natural events. One that fills the silence with intention rather than accident. The great silence may be deliberate. We are not alone. And the watchers have chosen not to interfere. This is the Zoo hypothesis. The idea that advanced civilizations, aware of our existence, have agreed to leave us alone, to observe without contact. We are a specimen in a cosmic preserve, a young species in a quarantine zone, not yet ready for the wider universe. The silence is not emptiness. It is protocol. The logic is straightforward. If even a single advanced civilization exists in the galaxy, and if that civilization has the capacity for interstellar travel or long-range communication, it would have spread across the galaxy by now. We should see evidence of its existence. Dyson spheres, engineered stars, megastructures, artifacts. The fact that we see none implies either that no such civilization exists or that such civilizations exist and are hiding. The Zoo hypothesis is the hiding explanation. Under this model, the anomalies we have been investigating take on a different meaning. Oumuamua may not be a natural object. It may be a probe sent to observe our system disguised as a rock. The hexagon on Saturn may not be a weather pattern. It may be a marker, a beacon, a structure built into the planet's atmosphere. The moons, with their impossible features, may be artifacts, remnants of an engineering project that shaped our solar system. The gravitational anomalies in the outer system may be the wake of something passing through, something we cannot see because it does not want to be seen. This is not science, it is speculation. There is no evidence for the Zoo hypothesis beyond the silence itself. It It is a story we tell ourselves to fill the gap between what we observe and what we can explain. It is a way of making the silence meaningful instead of empty, but it fills a silence that science cannot. The great silence is a vacuum. Nature abhors a vacuum, and so do we. We fill it with stories, stories about quarantine, stories about a universe that is not empty, but waiting. The zoo hypothesis cannot be tested. That is its weakness. It is also its strength. It cannot be disproven. If we never find evidence of other civilizations that is consistent with the hypothesis, if we do find evidence, the hypothesis is no longer needed. It is a perfect, untestable explanation for a mystery that will never be solved. A placeholder. A story. But a story that makes the silence bearable. The silence is not empty. It is full of interpretations. Every null result, every empty frequency band, every star that does not answer, they all carry meaning. The question is what that meaning is. We may be alone. The simplest explanation, the one that requires the fewest assumptions. The universe is vast, life is rare, intelligence is rarer still. We are the first. We are the only. The silence is the sound of an empty galaxy waiting for us to fill it. That possibility is humbling. It is also lonely. To be the only voice in a universe of 100 billion galaxies, to be the only mind that knows it exists, that is a weight we were not designed to carry. We may be watched, the zoo hypothesis, the quarantine. The silence is not absence. It is protocol. Someone is out there, and they have chosen not to speak. They are waiting. For what? We do not know. For us to grow up. For us to pass some test we do not know we are taking. For us to prove we are worthy of contact. The silence is a door that has not opened yet. We may be too primitive to hear. The signals are there. They fill every frequency, every wavelength, every corner of the electromagnetic spectrum, but we lack the ears to hear them. We are like a radio built before the invention of radio, listening for sounds that do not exist in our limited range. The silence is not empty. It is our own deafness. The wow signal is the closest we have come to breaking that silence. One moment in 60 years of listening, when the universe seemed to speak. A single word in a language we do not understand. And it gave us nothing but a question. No follow-up, no confirmation. Just a spike in the data, a circle in red pen, a word in the margin. The signal came, it spoke, and it never returned. Walk back through what we have seen. 5 anomalies. Oumuamua. The shape that should not exist. The acceleration that should not have happened. The object that moved like nothing we have ever seen. The hexagon on Saturn. A perfect geometric figure in a world of chaos. Stable for decades against every law of fluid dynamics. The moons of Saturn. Iapetus with its equatorial wall, Mimas with its impossible crater, Hyperion tumbling through space like a frozen sponge. The gravitational pull at the edge of the system, something massive herding the distant rocks, something we can feel but cannot see. And the signal, the one word from the void that never came back, the hydrogen iceberg, the standing Rossby wave, the thermal segregation, the planetary perturber, the magnetar flare. Each one stretches the definition of probable. Each one requires a special set of conditions, a narrow window, a lucky alignment. The patterns that look like designs, and we keep finding ways to explain them away. We are pattern-seeking creatures. It is our greatest strength. It is what pulled us out of the trees and into the stars. We see faces in clouds, meaning in noise, order in chaos. That ability built our civilization. It also blinds us. We see patterns where there are none. We read meaning into randomness.
The aurora,
We find
a dance of
design in
light
accident.
caused by solar winds
The solar
interacting with
system is a
Earth's
mirror.
magnetic
It
field.
reflects back what we bring to it. And what we bring is a desperate need to understand. Perhaps we are not yet ready to understand them. That is the hardest part of standing where we stand. We have learned to measure, to calculate, to predict. We have built instruments that can see across billions of light years. And still, when something arrives in our own neighborhood that does not fit, we are reduced to speculation. The tools that let us map the cosmic microwave background with exquisite precision cannot tell us what Oumuamua was made of, or why the hexagon refuses to break apart. The limits are not our instruments. They are in the nature of the questions. Some mysteries resist resolution, not because we are not smart enough, but because they were never meant to be solved in a single lifetime. The investigation continues. The next anomaly is already approaching. It may be in the data right now, waiting for someone to notice. It may be passing through the solar system at this moment, unseen, unrecorded, a visitor we will not detect until it is gone. The universe does not stop producing mysteries just because we are not ready for them. The solar system is our home. It is also a mystery. And the mystery is not a problem to be solved. It is a condition to be lived with. We will not find all the answers. We will not resolve every anomaly. We will not wake up one day and understand everything. That is not how it works. The universe is larger
Bathed
than our
in the
capacity
soft
to
amber
comprehend it.
glow of a distant sun,
It is the nature
the
of
Martian
thing
landscape reveals
to
its
stand at the
ancient
edge of what is
secrets.
known and feel the weight of what is not. To look at a data point that contradicts a model and feel not frustration, but wonder. That is what science at its deepest level asks of us. Not certainty, not completion, just the willingness to keep watching. The next anomaly is already approaching.